We'll now look at what happens to light when it encounters a boundary between two media. Remember, with waves, when waves encounter a boundary, part of the wave is transmitted into the second media, and part of the wave is reflected back into the first. That's the same thing that happens here with light. When light encounters a boundary, part of the light is transmitted into the second media, and the part that's transmitted is refracted or bent. And then part of the light is reflected back into the first media. So we'll go through how reflection and refraction of light work in this section. Okay, so let's start with reflection. There are two types of reflection. Specular reflection is reflection off a smooth, flat, reflective surface, such as a regular flat plane mirror or a shiny metal surface. And then diffuse reflection is reflection off of a rough surface. We're going to focus on specular reflection in this course. Specular reflection is governed by the law of reflection. The diagram for the law of reflection looks like this. We have the surface, this horizontal line, so that's the boundary between two media. And then we have our incident ray here, which collides or interacts with the second surface at the point of incidence, which is right here. And then it reflects on the opposite side of a normal line. So this dotted line here is called the normal line, and that's an imaginary line that's drawn perpendicular to the surface at the point of incidence. So that's the normal line, and normal means perpendicular, so that's why it's called that. Okay, and then we have theta I, which is the angle of incidence, and theta R, which is the angle of reflection. And we'll actually use degrees quite often in this section opposed to radians, so we can change our modes now on the calculator. Okay, so the law of reflection says two things. First of all, the incident ray, the reflected ray, and the normal line all lie in the same plane. So they're all in one 2D surface. That means it actually looks like this. I've drawn it on a surface of the whiteboard, and it all would be in one surface there. Then the second point, which is often what is considered on its own the law of reflection, is that the angle of incidence is equal to the angle of reflection. So theta I equals theta R, and that's a really important point here. Also, it's important to note that both angles and all angles in this section will be measured from the normal line, not from the surface. So the angle of incidence is the angle between the incident ray and the normal line. Example 1, two mirrors make an angle of 120 degrees with one another as shown in the figure. A ray is incident on mirror M1 at a 65-degree angle to the normal. Find the direction of the ray after it has reflected off of mirror M2. Okay, I sketched this again here. So the incident ray is here at 65 degrees to the normal, and eventually we want to find the direction of the ray over here. So let's find this direction as it reflects off the surface of the mirror. So this is 65 degrees. The law of reflection says if this is theta I, then it's equal to theta R, which is on the opposite side of the normal. So this is also 65 degrees. And then I want to use this triangle here to find this angle. So I'm going to need this angle here, which is 90 minus 65, since it's between the surface and the normal, and that's 25 degrees. Okay, so since we have a triangle here, we know that the angles in the triangle must add to 180 degrees. So if I want to find this angle, I just wrote theta in there. We'll have theta equals 180 degrees minus 120 minus 25 degrees. And that is 35 degrees. And then because of the law of reflection, we could find this angle here. So, well, first of all, we could find this angle, which would be 90 minus 35. So 55. And then this angle is also going to be 35 degrees, since we know this angle would be 55, and then this is 90 minus 55, or just because we have this surface and this ray has to reflect at the same angle here, also because of the law of reflection. So how you answer this, just be specific with the angle. So we could say 35 degrees from the surface of M2. Or if you're just going to give the angle of reflection, then it's this angle here. So, or you could say with an angle of reflection of 55 degrees. Example 2, a dressing mirror on a closet door is 1.5 meters tall. The bottom is 0.5 meters above the floor. A bare bulb hangs 1 meter horizontally from the closet door, 2.5 meters above the floor. Treating the bulb as a point source of light, how long is the streak of light reflected on the floor? Okay, so I've drawn a few diagrams here to help with the solution. This is the room, and then we have the bulb here at 1 meter from the wall, and then this is the mirror, so it's 0.5 meters above the floor, it's 1.5 meters long, and then 0.5 meters below the ceiling. So this is obviously not to scale. I'm just going to use it for the geometry. And then this will be the light patch. So the edges of the light patch on the floor will be created by incident rays. Well, incident rays on the mirror that then reflect. And the edges will be from the ray that hits the top of the mirror and that hits the bottom of the mirror. And then rays in between will make up the length of this light patch here. So we're looking at this from the side, so we're only looking at that horizontal length of the light patch. Okay, so we can just use geometry to find this based on the law of reflection. The law of reflection says that these angles are equal here as the light reflects off the mirror, and these two angles are equal to each other there. Okay, so let's look at these two diagrams. I've split this up so we can see the top ray. It hits the top of the mirror here and then reflects to make the far end of the light patch. And let's just look at this one for a second. So the law of reflection again told me that these two angles are equal. And then that means that these angles in here are equal to each other as well. Can I use 3 lines now? 3 lines. Okay. So those angles are equal. So we have similar triangles. Actually, all the angles are equal. So we have angle, 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 similarity here. So I'm going to set up a ratio for the similar triangles. I want to find x, the length here. So this is 2 meters because it's the length of the mirror above the floor plus the length of the mirror. So I have x1 over 2 meters equals the length of this side, 1 meter, over 0.5 meters. And we find that x1 is 1 times 2 over 0.5. So 4. Okay, so the far edge of the light patch is at 4 meters. Now, if you don't remember doing similar triangles or you're not as familiar with that, really what this is just saying that since these angles are equal, their trig functions have to be equal. So I chose tan in this case, and I'm saying tan theta, this is theta, equals opposite over adjacent. This is also theta, so we also have to have tan of theta equal opposite over adjacent. And then these are the ratios. Opposite over adjacent equals opposite over adjacent. Or you could find this angle and then use it to, or find this angle and use it to find the length here since it's equal to that angle. So more than one way, thinking about it as similar triangles is probably the shortest. Okay, oh, this is slanted, but let's look at this bottom ray. Hits the bottom of the mirror, so 0.5 meters off the ground, and then there's 2 meters above. Again, I'm going to do the same ratio since we know these angles are equal. So x2 over 0.5 meters equals 1 meter over 2 meters. So x2 is 1 times 0.5 over 2 meters. And this is a quarter, or 0.25. Okay, and those are the two edges of the light patch. So now the total length of the light patch, delta x, will be x1 minus x2, so 3.75 meters. Okay, let's now look at refraction. Refraction is the transmission of light from one medium to another with a change in direction based on the difference in speed of light from one medium to another. In order to do calculations for refraction, we need a new quantity called the index of refraction. The index of refraction is the ratio of the speed of light in a vacuum to the speed of light v in that medium. So c here is the speed of light in the vacuum, 3 times 10 to the 8 meters per second. The speed of light in any other medium will be less than the speed of light in a vacuum. So our index here is a unitless quantity, it's a ratio, and at the least, it's 1. It's equal to exactly 1 for a vacuum. And then in air, we have n is 1.00029. So we can also use 1, that's 1.00 to 3 sig figs for air. And then in any other case, we'll have n greater than 1 for other media. The law of refraction is called Snell's law. So let's look at this diagram between two media. We have our first substance with N1 and then the second with N2. And then light is incident in the first medium at angle theta 1. So generally the angles here are just labeled according to the medium number. So we could choose 1, 2, 3, and 4 if there were more different materials. So this is theta 1 and then we have theta 2. It's important to note that the light refracts or bends on the opposite side of the normal line. So it's not on this side here, it is passing through and bending on the other side there. And Snell's law is n1 sine theta 1 equals n2 sine theta 2. And this will allow us to calculate the angle at which the light will enter the second medium. Okay, I just want to go over two different cases. So case 1 here is when light is traveling from an index of n1 to n2, where n1 is less than n2. You can think about the index of refraction as an optical density. So it's going from something less optically dense to more optically dense. And the example I have is air to water. In this case, and you could check this with Snell's law, what we'll find is that the light ray will bend towards the normal. So theta 2 is less than theta 1. Now in case 2, the light is traveling from something that's more dense to less dense. So higher index to lower index. And the example I've drawn is glass to water. So the light's coming from glass, it's traveling to water, and in that case it will bend away from the normal. So theta 2 is greater than theta 1. So we can kind of tell how it will bend just based on the difference in the two indices. And also note that if theta 1 is 0, then theta 2 must also be 0. So if the light's traveling perpendicular to the surface, it doesn't refract. It transmits, but it doesn't bend. It will stay at 0 degrees and travel along the normal line. So you've definitely seen refraction before. Anytime you see something that looks a bit distorted in water, that's due to refraction. So if you put a fork or something in your glass of water and it looks bent, that's refraction. And if something appears to be a different height in water, so someone's standing in water and maybe they look shorter, this is also due to refraction. And we'll talk about more applications of this in the next section. Oh, one more thing I wanted to add is that the index of refraction is a constant for that medium. So if you're not given that constant in the question, you can look it up in a table for the index of refraction, and there's a table on your formula sheet, or in the module 4 problems, there's a table there. Sometimes we solve for it if it's unknown, but otherwise we can look it up for that substance in the table. Example 3, a laser beam is aimed at a 1 centimeter piece of crown glass at an angle of 30 degrees above the surface of the glass. The index in the glass is 1.52. A, what is the laser beam's direction of travel in the glass? B, what is the laser beam's direction of travel on the other side? And C, by what distance is the beam shifted from its original direction of travel? Okay, so I've drawn this out here. I used a ruler. So we've got the incident ray there. Incident at 30 degrees above the surface of the glass. So this isn't the angle of incidence, it's that angle in there. So we will need this angle here to use Snell's law. So this is going to be 90 minus 30, which is 60 degrees. Then I've drawn in the normal line. Mine looks a little slanted, but it should be at 90 degrees perpendicular to the surface. Okay, so then for part A, we can apply Snell's law. So I'll just do it up here. We have A. N1, so it's N1 sine theta 1 equals N2 sine theta 2. And we have air, so N air sine theta in air equals N glass sine theta in glass. I'm just using subscripts really to relate to part B. But now we want to find this angle in the glass. So we'll have theta glass, if we rearrange, equals sine inverse 1 sine 60 over 1.52, which should give 34.7 degrees. So that's our angle right here, this theta glass, which was 34.7. Okay, so for part B, now we want to apply Snell's law at this boundary. So the light ray travels through the medium. Notice it did bend towards the normal, which is expected when it's going from a lower index to a higher index medium. And now it's going to intersect here and refract out of this piece of glass. So if we go to apply Snell's law again, now we'll have n2 sine theta 2 equals n3 sine theta 3. But if I use the same subscripts here, well, let's trace the angle through in the first place. Notice this is theta g. These are two parallel lines, and we have one line crossing those parallel lines. Or you can see this Z shape here. So this is also theta glass. Those angles will be equal. So that will be our initial angle. So we'll have n glass, now that's n2, sine theta glass equals n3 is back to air, sine theta 3. And notice that this is the same as we had originally up here, n glass sine theta glass, and we still have the index here of NA. So you could plug in the numbers if you want. You're going to find the same thing. So this will give that theta 3 equals theta 1, which was our theta in air, so 60 degrees. So since the surfaces of the glass are parallel, Snell's law shows us that the light will again refract at the same angle that it was initially incident on the glass. This is different for prisms or shapes where the two faces aren't parallel. Okay, so part C, by what distance is the beam shifted from its original direction of travel? So if we extend this incident ray on the glass, it would have originally been traveling here. Now when it refracts, though it's at the same angle, so these two lines are parallel, it's been shifted a distance d, this perpendicular distance, from the original direction of travel. And that's what we're asked for in part C. So it's hard to solve for it if we have it here, but we can move it here to this point of incidence of that internal ray. This is still d since they're still parallel at that point. And if we do that, since it's a perpendicular distance, we have a right triangle here. And we can use some geometry to find that. So I want to also use this triangle. I'll just extend this dotted line so you can see. We have another right angle triangle here, and we also know this angle. So we have two triangles in a sense. Let's call this L, this side L, and this angle alpha. And so first we'll use this triangle to find L. So I'll write it down at the bottom. Just flip down for a second. Okay, so our triangle looked like this. Just briefly, I'm going to sketch it. L, this was theta in glass, and then this is 1 centimeter. So we're told that the thickness of the glass piece was 1 centimeter. So then we'll use cosine, and we'll have L cos 34.7 equals 1 centimeter. So solving for L, we have 1 centimeter over cos 34.7, which is 1.21 centimeters. Okay, great. So now with that, we can use it back in our diagram here. On the second triangle, now it's the hypotenuse. And we can also find this angle alpha because we know that this is 90 degrees here, and this angle in here is 30 degrees because that's this angle just crossing one line, so it's an alternate angle from our incident angle to the surface. So then we have angle alpha, which is 90 minus 30 minus 34.7, so 25.3 degrees. Okay, so then our second triangle that we're looking at is on the other side of L. Kind of like this. This angle is that 25.3 degrees. This is L, and we want to find D. So we have D equals L sine alpha. 1.21 centimeters sine 25.3, which is 0.52. So anytime you're looking at the distance that a beam has been shifted through two parallel lines or a block with parallel surfaces, you can use this method. And I would remember this because in the lab we will be looking at refraction through a block and we'll need to find the distance that the beam is shifted there. A light ray traveling in air is incident on one face of a right triangle prism made of a substance for which n equals 1.5. The ray follows the path shown. Take angle theta to be 60 degrees and note that the base of the triangle is mirrored. Determine phi, the angle the outgoing ray makes with the normal to the surface. Okay, so it looks like this. We have this vertical ray that's incident on this triangular prism, and then this whole surface at the bottom is mirrored. So this question is really about just doing a bit of triangle geometry and then applying Snell's law at each surface. So this is 60 degrees, and we have air out here, so n is 1. And then inside, it's going to be, I'll write it here, n is 1.5 for the prism. I'll call it G. It's probably glass at 1.5. Okay, so now let's find this angle by applying Snell's law. So our first step is to apply Snell's law at this first surface. So we'll have n air sine theta air equals n glass sine theta glass. And then we get theta glass is sine inverse of 1 sine 60 over 1.5. And that's 35.3 degrees. Okay, so now first we want to find alpha and then apply the law of reflection. So this ray will travel here, pass through the prism, reflect on this bottom surface, and then reflect here, and then exit the prism. So I want to use this triangle in order to first find alpha. So I want the angle here. I know now this angle here is 35.3 degrees, this one. So to find this one, I'm going to do 90 minus 35.3, which is 54.7. And now looking at this lower triangle here, we know this is 60. So to find this angle, I'm going to do 180, since all the angles in the triangle add to 180. So 180 minus 54.7 minus 60 is 65.3. And then if you look carefully, this alpha here, this is 90 degrees since it's to the normal. So we'll have alpha is 90 degrees minus 65.3, 24.7. Okay, so we have alpha. There is more than one way to find alpha, so if you figured it out another way, that's great too. You could extend this, for example, and use this upper triangle. Okay, so this ray travels. This was hard to draw because this is a really small angle in here, but it will reflect at an angle to the normal. It'll refract, and then it will refract outside of the prism. So, all right, let's use some more geometry in order to find this angle in here. If I look at this triangle, this is 60 degrees here, and then we have 90, so this has to be 30. And then that means that this total angle, so what I want to do is draw in a vertical line here so that I have another right triangle, and then I know that the angle in here is going to be 60. Okay, so that's 60. Why I'm doing this is because I have alpha, and alpha was the angle to the vertical. So when we draw this line in, again from this line intersecting two parallel lines, or the Z rule, we know that this is alpha inside there. And this is all a right angle. So in order to find this angle here, let's call it theta prime. I have theta prime equals 90 minus 60 minus alpha, which was 24.7, so 5.3. Okay, so it is small, that's why it was hard to draw. But again, I wanted to extend this vertical line because that's where I have alpha. That's how I can find this alpha reference on this side. And then it's nice because I do have this right angle triangle, so I can use this 30-degree angle to find 60. And then we subtracted to find 5.3. Again, there's probably another way, but this is the one that seemed to make the most sense to me. And now we're almost done. So the last step is to apply Snell's law at this last surface here to find phi. So we have n glass theta prime, supposed to be sine theta prime in glass equals n air sine phi. So phi will be sine inverse 1.5 sine 5.3 over 1. And that's 7.96 degrees. You might have a bit of variation based on how you rounded, but you should end up with something close. Okay, let me know if you have any questions.